русскими финтами там проблем нет. Я читаю, там все поделено на троих. Сергей Аркадьевич, Ольга Алексеевна и я.
А, то есть Сергей Аркадьевич тоже нам будет, да? Что-то
нет, он здесь не будет по-английски, он не любит, видимо. И в итоге это все на нас свалили, с Ольгой Алексеевной. А в прошлом году читал еще Архипов, а сейчас он то ли уехал, то ли что. Поэтому у меня были только практические занятия. Поэтому в веб-сайте я тоже не до конца доработал. Кто Михаил?
Да.
Я вам на почту послал, проверьте ссылку на этот сайт. Вообще можно сделать телеграм-канал. Обычно мы так делаем. Если вы его создадите, то я вот сюда его впишу.
Да.
И все будут знать, те, кто опоздавшие и все прочее, они будут в курсе.
Сделаем.
Вот. Окей. Ну ладно, давайте на английском буду говорить, как положено. Значит, this is website which is related or responsible for my part of this course, Femtosecond optics, femtotechnology. I deleted the description which is related to the Olga Smolyanskaya because it's previously in previous year it was divided for specific dates, but now we have only tables like that, which reflects the lectures and practice which were responsible for me and for Olga Smolyanskaya. The blue one is my part of the course. You can see it's intermediate attestation is here, and the second part is Olga Smolyanskaya part, and we discussed that previous two lectures should be here, and now as I understood I replace this laboratory works, yes, and have you classes in 7th February?
Yes, we had
laboratory work.
No, we had with Maxim.
Maxim again give you second laboratory work.
Yeah, first and second.
Okay, so in this case, I suppose some of these laboratory works will be shifted to here. Maybe she will ask me to, for example, in this Wednesday, you have two laboratory works. Maybe I should replace it with Maxim, but in any way, now we have my part of the course, then you will have the part of the course of Professor Olga Smolyanskaya. And what additionally important that usually I have 4 or 5 lectures. I have a lot of materials on femtosecond optics, femtotechnology, but probably most of presentation and description in Russian. So usually I have some lectures. I give you some lectures, and after that you prepare some individual project. It's the requirement for this is reflected there. Yeah, you can write it in detail. So usually I give, for example, we have 6 students. I have 6 topics. Prepare Google Disk space for that. Give the links here. Now I not attached it, but maybe I will do it maybe today evening or similar. So usually it is some papers. You read some papers and prepare the talks. It's first variant. The second variant is preparing the lectures. So maybe now it's more relevant to do the lectures because I have a lot of lectures in Russia, and usually I ask students to read take this material and then improve it somehow. So it means that it's written there quite detailed as I understood, but maybe I'm not. You work on component, you will be graded on the several directions. For example, slides designs, components in the abstracts, synapses. So you create like some conspect of these lectures. It's usually includes the slides and description of each slides. Usually it's absent. Now maybe some lectures have this description in Russia, but in any way it could be optimized and maybe refurbish it, I don't know how to say, reprocess it by you. And in this case, later we will have practices and you present what you have done, maybe some summaries, and after that I also ask you prepare some questions. We post these materials on the website, and all the students should pass the questions which you prepared. So it's like kind of active learning and so on. So in this case, the grades will be each student obtains grades for laboratory works given by Maxim. Yes, maybe if you have additional experimental
yeah,
it's
with
also
you
will be graded, but it's not my responsibility. I also take the final grade for my parts of the course, and it will be summarized with your grades from laboratory works, and maybe because this year Olga Smolyanskaya is the last who have lectures with you, she will take into account my grades, laboratory works, it will be like passed or not. Yes, and after that she will give you final grade from the course. So here I suppose that you should complete all tests. Yes, so what you have personally, all of you will give this question, so the others will address these questions, and so I give you some introductory lectures, and it will be the same maybe, but maybe I will go now shorter, and maybe you will in your part of the lecture you can review some questions in more detail, something like that. Okay.
Okay.
Good. For example, in Russian Femtosecond optics, the site is more detailed. I have questions there, but this year we, because usually this whole day I intended to prepare it, yes, but now Olga asked me to shift it, so maybe this year it will be a bit restricted. But another question, will you visit my another course of digital holography in English or not?
I guess yes.
It will be in the April.
Yeah, in our specialization. Yeah, most of 5 of us will have.
That's good, but in any way, again, in digital holography, I have a quite big course description and so on. Like on the website, it's much more elaborated, because I have already give this lecture and practice in English. But this year we also again some novelty, because we invited Professor Ostom. It's the famous holographers, maybe not famous, but one of the important researcher in the world. He worked in Stuttgart University and was head of one of the institute near there. And now he will ready to visit us. He retired, so that's it's no limitation for him to visit us. And he give you lectures in English, and it will be 5 lectures, as I suppose, in person. After that, he will need go to some meetings, and he give you in online in the, after the MICE celebrations day, something like that. So it's also will be novelty, so no this website, but for Russian group it's will be presented like that. Okay, what is important for you right now? So regarding the schedule, it's approximately like this. So we have 2 lectures today and maybe 2 lectures tomorrow, and I think the last maybe I don't know. You have a 6, yeah, maybe 6 lectures for you to present your materials, your improvement. It will be good. So we will start from these lectures, and if someone would like to prepare work on the project, it's also possible. You should let me know, but I suppose that it's better now to translate these lectures and change the slides, because the Ritmo style corporative style also changes. So now I have old lectures, so you will help me with that, and by using it, you I suppose that you better will learn the material, because you will work with it and to prepare the questions, so on. So I think it's more important that if I will speak very fast and you will not understood, catch it, and forgot everything. So maybe it's better that you work with your own with this material. Okay, this I think this all was about organizing. So now it's the requirement about plagiarism. It's maybe also common. Previously, sometimes I used when you will prepare the synopsis of your lectures. I can show you. I think how it looks like right now. Give me only, I don't know. Second optics, let's consider, for example, previous year, one of the previous year. It's like practice. Yeah, you can see it's conspect in Russian, maybe. Yeah, so there is a lecturers. It looks like that, for example. It's my lecturer. Yeah, today maybe I will show you, maybe this day, maybe tomorrow. And this is a conspect, so you see some of the parts of the slides. It could be like that, images from, and the description in the text, which you need to prepare for each slide. So it looks like study guide. Yeah, you have some slides, but usually it's quite difficult to understand what. That's why you're asking to write video, but maybe video it's also not easy. To when you have a lot of videos and you need to find a lot of information in short time, it's better to have in text form. So that's why I'm asking you to working with that and add some information to here. And finally, usually most of even good lecturers and researchers, when explain the material, give it in simpler form. But when you prepare it like in this conspect, you not it's like stenographic work on what the lecturer said. You need to instead you need to write the material and try to find some important things. Now I know everyone interesting with GPT-3 neural network. So I suppose that you can do it, but it's not be shot automatic way, because now people who don't know about this neural network, it seems that you just ask, oh, give me this material, and after one request it give it to you. The fact that I tried to work with it previous months, and the fact that it's not so easy to prepare high quality material. So we together you will present it, and we will see your conspect and your presentation, and finally we will review that. It's usually neural network gives very common phrases. It's lack of detail, sometimes a lot of repeats. So this text again should be optimized many times if you would like to obtain a high quality product. It should be a lot of works even with neural network. So it's like only two, for example, like calculator or MATLAB or something like that. So you can use it, I think. But of course, not think that it's help out of your problem, because the grading criteria here on the website is quite detailed. You can see where is it here. For example, 0 points that slides are not prepared, or slides that cloged with text, fonts, background color, so it's not good. But if you have, for example, would like to obtain 5 points, that slides allow to quickly receive the material, perceive the material, yes, complex ideas, everything should be structured. And for structuring, for example, you can ask a neural network, for example, you can give them a lot of information and ask it to help it classify it and so on. But after that, finally, you need to make a final check and maybe delete some wrong, something correct, because sometimes they not understood. It's not like a mind.
It's a machine.
It's machine, and it's only splits on the small parts. But sometimes it's easy to. I found that some of my students whom I asked to prepare thesis or for conference, something like that, the neural networks sometimes do not so bad results. But finally, I also often ask to correct it and so on. But in any way, it's required to use VPN for Russia. I don't know how you work with that. So it's also the complexity. Okay, so I think it's much more clear regarding the homework. So you need to prepare the slides, you need to give the talks, and you need to present the something like conspected, like that. Yes, with some description. I already can give you this material, so it's not the task will be only translate. Maybe I will mention which is bad, which is could be replaced. But finally, you should in your presentation you should explain this was not so good, and I decided to improve it in some way. Okay. Okay, so this was example, and I need to open the lecture. I don't know why it's not working fast. Like this. Okay, and I'm going to folder of this here. And today we will consider the first lecture. Usually it's quite, how to say, popular lecture. Not popular among students. I mean that popular, that it's not focused on the special things. It's like a review of some applications, and in general the aim of this lecture is give you understandings why it's necessary to use femtosecond optics, and it's part among the other things, among the, for example, what is a femtosecond? Do you clearly understand what is it, for example? Could you imagine, compare it with another intervals and so on? So this lecture addresses this question, and maybe I will, it's already, I have usually a bit shorter variant, but I took, especially for you, took big variants which already contain some information from students who add it already in Russian here. So maybe I will miss it, or maybe we will have comments that here you can work with that, improve and present this material in your personal power. So finally we will listen this material twice, yes, because I give you the basics and you repeat the main things, and maybe add some your detalization. Okay, how to say it's a demonstration in full, like this, I think. Yeah, okay, we will start from that. The first question is time interval, which is mankind is able to work. Yes, and this is a whole part of the lectures. Maybe, I don't know, it contains 15 slides, 50. So maybe it's will be split on 2, or maybe I will miss some materials, and I have also the other lectures which are already prepared in English. Maybe we will speak about mod locking and Q-switching. Okay, first let's start from interval. So you can see that seconds, it's from Latinian secunda. It's a measure of time, which unit of time measurement, yes, which is originated from this pars minuta secunda. It's second part of the hour, so because minutes is the first part of the hour, and finally it was reviewed that the second was the most earlier observation of the second. It's related to 1,000 years of yes, and it was Persian scientist Al-Biruni. He's divided the second as this part of the like a statement stated from this definition, and of course hours also was measured very approximately by the sun movement around the Earth, and people see at that time thinking that the Earth is not around, so it was like only observation. Well, what is it? And the first step tends to creation the hours with second arrow. It was not exact. It's related to this year. Yeah, and the year 100 years later, approximately, the mathematics proposed, Marie and Mersenne proposed to use oscillator with this length. Each have how to say oscillation time 2 seconds to define this to define this time unit. And later the Gauss move to the second, start to use, propose to use this in like basic units together with the meters and maybe candela, some physical units which is used for the in the main definition. After that ampere, yes, and so on, which was used in standard units of I don't know, в общем, в институте метрологии это используется. Okay, and maybe later it was a big progress in new technologies, and now we know that the second is defined as a period of oscillation of atom cesium. Yes, because it's specific time of oscillation, so you can count the number of oscillation. It will be much more exact, and in the end of this lecture we will should approach to this description is atomic clocks. Okay, this is a chart which describe. I already not remember the books from which it's taken. It's some books on femtosecond optics, and you can see maybe not femtosecond, maybe later. You can see that it's how it reflects approximately some minimization of time interval which researcher is able to work. And here another important chart which reflects maybe the main things of this lecture. It's reflected on this diagram, the main idea, because you can see that there is time interval and there is scales of the physical objects in our universe. And you can see that, for example, it's 1 millimeters, 1 meters, and it could also be extended in this way in the bigger objects like galaxies, universe, and so on. And also there is a specific time scale for this object. But now what is important for us in the femtosecond, yeah, you can see it's somehow related with these scales of the object, because it's easy to understand that when the object is big, it have some of inertia, so it's enable the big objects not able to move very fast. But if you minimize the size of the object, you minimize the mass, its mass, and this object is able to move faster. And if we going on through these physical scales, you can see that it's not a direct relation. That's 1 millimeter is corresponds to 1 milliseconds. Yes. For example, here some of experiments, and we will now we are able to go through all these time scales and approach the femtosecond and consider what happened in each time scale. Okay, and maybe we can start from millisecond. You can see this slide. It's what is possible to do. Some experiments which is possible to do with femtosecond. Millisecond time scale. But maybe this image is more interesting. It's not included in this slide. You can do it in your improvement of the lectures, because this is the first experiment which maybe how to say, originated the, it's not originated from the second optics, but it's originated the direction of science where researchers try to measure very fast intervals, seriously measure, because of course previously I showed you that maybe Gao, mathematic Marianne Mersenne have some definition, but serious complex experiment was performed. I'm not remember, maybe sorry, I forgot the last name of this man who do it. I know that this was in the Stanford University, and this guy have a party with the head of or rector of this university that it will be measure so the discussion was about when horses in gallop do our legs of the horse, at least one of the legs of the horse stay on the ground, or maybe there is some period of time when the horse like flying, and so the researchers not able to measure it, or some people thinking the horse is flying in short time, the other things no, and finally this guy performed the experiment. He drafts a lot of lines on the horse way, and these lines launched the photo flash with short time and photo fixation. So when horse movement is moved, he touched this line and the flash happens, and this moment was collected on the photographic films, and after chemical processing it will be like movie when the horse in our position. Yeah, it was found. I already forgot that it was found, but finally it was found the horse, yeah, it's like flying in some period of time, if I'm not mistaken. So it's not stay on the yours of whole time. So there is a moment where the horse is flying. Yeah. Okay, so it's the first experiments. It's already maybe one with 1500 years ago, and this is what's done in previous year. Now you have the simplest photographic camera with mechanical shutter, able to provide you experiments with something like that. You can because the duration of you need a very good light illumination of your object, because the sensitivity is limited of your photographic camera, but you're able to do the experiment like that in your mirrored camera. And the other example is holographic ARP. It's located previously in our Museum of Optics. We do it. It was idea of Professor Stafeev. He looked at in another museum, maybe in Shanghai and somewhere, that there is a possibility to visualize the string oscillation. And if you put some laser diodes behind these strings, and will match the frequency of oscillation these diodes with frequency oscillation of string, you will see the stable waves. Because now when you touch the string, you see your eyes is not possible to see all oscillation. It looks like blurred and for position. But if it's like a stroboscopic effect, you will irradiate the strings in specific time position. You will see the like sinusoid of the strings. So it's a very beautiful experiment, very simple. So everything what we have done, we buy a big balalaika, give it to specific woodworkers who put inside these diodes, and not to destroy this instrument, and we connect these diodes to the signal generator, and you everything what you need to you adjust the knob and find the touch the string and find the frequency when the wave is stable. And looking on the frequency, you can measure even measure on this knot what frequency you selected, and you are able to measure the frequency oscillation frequency. Okay, another example is stroboscopic effects I already discussed, and maybe time, how to say развертка, do you know in English? Time, okay, forgot it. Time resolved is like, yes, it's with resolution in time. Yeah, we will speak about it later a lot, but there is a specific word which used in the electronic tube of lamp television, televisors. So, for example, your eye is usually working with a frequency maybe hundreds of hertz. Yes, because maybe you already not catch this time, but easily to remember when it was not LCD displays, but very big with electronic lamps. There is a time of this oscillation of these devices, and if the cheapest one is 16 hertz, the most expensive it was 100 hertz. And if you have 16 hertz, it's not strongly visualized for eyes, but eyes is tired because lack of oscillation. And I know now this effect is easy if you're going to the media market on I don't know what shops we have now, where they sell a lot of displays, LED even. You can come to this LED where this place where they demonstrated a lot of displays in one time, and because each devices have even LED LCD monitors have frequency oscillation, but each device is not matched their frequency oscillation with another match. You see that it's not comfort. You perceive. You will have not good feelings for your eyes, so you feel this small frequency of time. And watches. Another interesting observation for me is I just maybe you know that the flies very fast, yeah, and so they live in maybe shorter time scale. And if you imagine these lamps, this oscillation also have 50 hertz. So maybe for fly, it's this oscillation is should. I believe that they should resolve this oscillation. It looks like the fly going to this room with this luminescent lamps or so on. So they going like a dancing pole, like the dance pole, because it's no. I believe that they should resolve this. Flash, so it's.
So we are very slow for them, yeah. That's why it's hard to kill them.
Yeah, but it's one of the ideas what happens in milliseconds. So let's go to another shorter time scale, and here is still possible to use by simply devices what we have now, like photographic camera and so on. But microseconds it's -6. But I already should speak not about devices like this mirrored camera. Yeah, there is another kind of shutters, it's electro-optical shutters. And the duration electro-optical shutters for this camera reach nanoseconds. So in microseconds it's easy to study some some processes. And this is some examples. I think this is examples maybe even as mirrored cameras. This is already more complicated examples. It's like disintegration of the how to say
drop.
Drop, yeah. Water drops, and with microsecond resolution, and there is some actions of electronic or magnetic fields on these drops. I think very high power electronic field. And it's this image is taken from this review, so you can read it for more information if you like. And there is, for example, why researchers do that. For example, you can see that you able to study some jets, yes, in this resolution. And why it's important? It happens that investigation of such jets can obtain some findings for development mathematical models and so on, how to materia spread it in universe. So this is some simulation how the mass is distributed all in the universe, in galaxies and so on. So sometimes it's information could be validated in experiments with jets, because it's also if you have specific nozzle, yeah, the drops will be spread in a specific way, and each could be so you can this z-axis you can adjust, like not adjust, define that this is time scale, and you can create things that it's like evolution in time of one of the drops, something like that. Okay, so it's half of experiment. It's of course it's just one of examples. A lot of things which happens microsecond time scale. Some slowest electronics processes already start to in this scale. For example, heat transfer is also in the edge between microseconds and nanoseconds, so something there. And microseconds. So another experiment is which is possible to investigate is like it's bionics and so on, where when a researcher trying to match the movements of their machines to do it much more natural, like in examples what we have in the nature. Yeah. So they investigated hummingbirds, it's colibri in Russian. These birds have very fast oscillation of wings, and there is a specific techniques which is called particle image velocimetry. When you add in your jet or in your for example, they try to study water jets, air jets, which is from the produced by these wings. Yes, you can add a lot of particles and use laser flashlights like stroboscope, and you measure the, for example, 2 or 3 exposures, very short exposures with some period of time, and you able to calculate the correlation coefficient between how each water molecules, not water, it's like maybe special paints, special paint particles move it from one part to another part, and if you process these images like in MATLAB and somewhere and try to calculate correlation coefficients, you will see that if you, for example, you have a big photo, you divide it on the small parts, and each part of this image represents the reflects the general movements of particles in this specific parts of the image. So you can try, instead you can calculate the shift of the correlation coefficients, which is reflects the direction of the movements of each lines, and finally you take like vector plots, a lot of arrows, which indicates in which way and how strong the movement of particles in each position. And finally you obtain information about the movement of the air of these hummingbirds. And this is some examples of various how to say, it's insects and birds. Yeah, you can see that these some birds use spread the air flow in the direct direction, and insects have a 50-50. There is some parts of air going forward direction, part of the backward direction. So it's now very important, as you can see, that for development for various aerial or man-made devices. Yes, how to say this word? Aerial on man-made devices, maybe flying devices, something like that. So it's this knowledge is taken into account in these directions. Okay, so it's another applications. And some more examples in this time scale. So some experiments in ballistics, for example, when you try to develop something which should be strong from the bullet and so on, you able to adjust, for example, 4 cameras with small exposures. It's like these experiments of it's not Talbot. This gentleman who measures the horse gallop.
Mm-hmm.
You launch it serious exposures with very short exposure, several cameras, with some exposures and very short, and you can visualize the dynamics of the process. It's like that. So it's like when you put your flat plate to the liquid, you can see what happens, or another ballistic experiments like that. It's taken from the website of, this image is taken from the website one of the Moscow company who produce such cameras. We also do that, and it's also images taken from this fast camera, this fast electro-optical shutter. We already moved to nanoseconds time scale, and you can see the whole of our red house in the first floor. We have a range-gated experiment. So we have nanosecond laser, which will duration have maybe 9 nanoseconds, if I correctly remember, and we match it with this ultra-fast camera. It's not ultra-fast, it's nanosecond camera, but it's one of the fastest camera what we possible to invent, because of the other experiments in shorter time scale will be only with, like, not direct. We're not able to visualize a direct process, but I will explain later about that. But now it's one of the fastest direct experiments. So we have direct observation, the laser pulse going forward direction, reflects from this piece of sheets, piece of papers, sorry, and reflects from various in various positions, in various time scales, and we able to accumulate the signal from the specific locations. What is more important in these experiments, we require to take into account the length of the wires, which wires our lasers and our camera, because if you have a very long wire, the signal from your generator will be spread over the wires sometimes, and you obtain shift of your measurement not in the exact time. So it's already important in these experiments. And you can see that for the 1 nanoseconds, you know the speed of light, and you can calculate that the light transmits only 14 centimeters. So it's in the real world we have quite measurable time scale, but in the time scale we already work with a very short duration because of limited speed of light. So in these cases, one of the important principles is that we convert light movements from the very short time scale to the more easy measurable spatial dimension. Yeah, it's one of the important parts. And so what I can show here else, it's nanosecond. So for example, we have some project trying to develop some LIDAR which able to absorb some useful gases for in the water. So we have laser, we have camera, we match it with spectrometer, and a laser have nanosecond pulses which going to the deep or white water volume. And if in some positions we have some useful gases, there is some specific nonlinear processes which produce another radiation in another wavelength, and this radiation, because of limited laser excitation time, it will be this radiation also will be produced in each position in specific time. Yeah, that's why we, if we will use a range-gated spectrograph, we will measure. It's shown like that. We will have, this is a wavelength scale, yes, and this is a range. So in various ranges we will able to measure the spectra, and you can see that there is a spectra of concentrated CO2 in water. It's some peaks, and some peaks could be, for example, CO. For example, it's H2O, it's CO2. There is some peaks which reflect that in this range. Within the range, we will have the source of this gas. So it's used for finding these useful gases in water. Okay, and we're going forward to the picosecond time scale. You can see 1 picosecond is already quite difficult to imagine in the macroscopic objects, but in physical scale the light passes only 300 micrometers in this time scale. It's easy to remember, and 300 micrometers is the thickness of your paper sheets or hair, something like that. So comparable thickness, and you can see that in these time scales we still have some it's not fully microscopic, but maybe it's closer to microscopic scales, but it's in the edge between the microscopic time scale and microscopic time scale. Yeah, so there is some quite big oscillation of crystallic grating.
Lattice.
Lattice, yeah, I forgot this specific term, sorry. And there is a kinetics and solids, and kinetics and semiconductors. So, and you can see, maybe you're already familiar with terahertz radiation. I think some of you should know about it. And we will speak about it more, and I think Olga Smolyanskaya will have a lot of application of terahertz radiation. So, in medicine and so on. And terahertz pulses have a duration, one oscillation of terahertz pulses, it's coincide with picosecond time scale. It's not exact 1 picosecond, but 1 terahertz, frequency of 1 terahertz, it's matched with the wavelength 300 micrometers, and the terahertz radiation, which accumulates a lot of pulses at various wavelengths. It's a broadband in its nature. Its contact include the pulses with various duration. And it covers or 1 terahertz frequency is less and more, something like that. Okay, so and here what is again important, it is not possible to use photographic camera directly in these time scales already, and starting from this time scale and shorter, but there is a very useful technique which is called pump probe. This the pump is initiates some repeatable process in the system. The word repeatable is very important here. In one conference I observed a discussion with one professor who is not working with this femtosecond and time scales. He didn't understood how it works because the young researcher who is making the talk not forgot. He's forgotten to say that this process must be repeatable, because you have in your system you're able to produce equidistance. We will discuss it in framework of our course. Equidistance pulses, which is coherent. One pulse is coherent with another pulses fully, absolutely coherent. So that means that it's able to interfere and so on. If the process which you launch it with that pump approach, for example, you have laser oscillation 1 hertz. Mm-hmm. Yeah? 1 hertz. You divided your pulses in 1 second, and if your time process absolutely decrease and stopped within this time interval, you the next pulses will repeat it, and if you need not destruct your object or sample, you will able to shift the delay line. If you measure, if you see that 1 picoseconds in only 300 micrometers, it's easy to match the mirrors in our system, yes, and shift mirrors a bit. We will, for example, obtain interference of two signals already in a bit another temporal position, yeah, in the scale of picosecond scale. It's, if the process is repeatable, you will able to move your mirror in delay line and scan the whole process, and thus obtain information about the, for example, keeping chemical reaction and so on. Some examples will be provided later. And okay, so we have two pulses. The probe pulses, of course, read the changes which happens with your systems. Maybe a question to you: how you imagine what means reads the changes? Because it's a very common words, but it's you need to obtain some details, to imagine some details how it could happen. What changes?
Changing of some properties, maybe of refractive index, of absorption.
It's properties of the sample, but I mean what happens with your probe pulses. For example, the pump changed something because of this process, and you would like to obtain in a specific time position, yeah, observe it. What happens the next? What happens with probe pulses? One of the because we say that it's a read this condition of the sample, but how it's do it physically? What happens with pulse?
Maybe it can be amplified, or it can be absorbed, or maybe yeah.
Reflected, absorbed, yeah, a lot of processes. No, maybe another examples. How many parameters do you know of wave?
Phase, intensity, frequency.
Yeah, all of that could be the source of the useful information. For example, in one experiment, the pulses could change their polarization. In another experiment, for example, I will show you maybe in the next lecture, dioxide vanadium, I forgot, dioxide. Vanadium contains very similar two similar kinds of lattices, which is the first lattice is transparent for radiation, the another one is reflected. And if you add some voltage to the dioxide vanadium, you will change its structure very fast. In 100 femtoseconds, you will obtain it's like a reflectable lattice. So in this case, you can first of all the researchers studied, and now they applied it for useful shutters and so on in femtosecond optics. Okay, and some of examples of applications, so relaxation of the matter in the initial states and the time of the relaxation and so on. A lot of nonlinear optical processes like Kerr nonlinearities and so on. By the way, Professor Kozlov already gave you basics of nonlinear optics.
Yeah, on the fourth course of.
Yeah, so you know what is the Kerr effect and so on.
Yeah,
that's good. That's good. Okay, so this is examples of picosecond interaction. It's like you can see it's how to say, I forgot. Excitation, yeah. Excitation, luminescence, and each takes in specific times. For example, luminescence is quite long process, but so there is some maybe 2-photon absorption and so on, which faster from, as you know, from the basics of nonlinear optics. Okay, and we approach to femtosecond time scale, and here you can see that in 1 femtosecond corresponds only 300 nanometers. It is less than wavelengths of visible range, yeah, because visible range radiation started from 400 nanometers approximately. Yeah, so it's less than wavelength. That means exactly that 1 femtosecond. I may be asking you what follows from this. That's the duration of the time scale of 1 femtoseconds less than 300 nanometers. What follows from the what conclusion we can make according to the femtosecond optics, femtosecond laser pulses? Will be able to? Yeah. Not.
If I'm not mistaken, we generate femtosecond pulses in infrared region 800.
What you can create, you know nonlinear optics, you know about the process like second harmonic generation. Yeah. So you can obtain from infrared pulses, you can go to the visible pulses. The second harmonics, it will be of titan sapphire laser. It's directly like blue radiation. Yeah, it's 400 closer to ultraviolet for 400 nanometers. So it's visible range. So we can produce it. But what about durations of these pulses? We'll be able to create second harmonic pulses with duration 1 femtosecond.
Sounds like no.
Yes, I think you're right. But unfortunately, the previous lecturer of these courses in English, Rostislav Arkhipov, their topics of their research is the oscillations of the ultrafast oscillations, which is less than 1 oscillation. So it's half oscillated laser pulses, for example, which contains only positive parts without negative parts, like kind of solitons. They tried to predict it in some theoretical matters, and I believe that it was the topics of previous lectures in this discipline in previous year, for example. But unfortunately, it's not mine research topics, and I don't know, that is quite difficult. I believe that the durations of 3 femtoseconds, I know it's exactly, it's very difficult to reach, and what is more important, it's able to reach only a specific position of space, because air have introduced a lot of dispersion in so small pulses. So if your pulses will propagate it in air further, because of this dispersion, some parts of components of this light, of this radiation in this pulse will be have delay, will be delayed, and another one will be not so strong delayed, or delayed with a bit different retardation. So that means that in this position of time you will have 3 femtoseconds, but maybe after 2 meters you will have already 4 femtoseconds. It's there is exact equations to calculate it. I can recommend you to use such company T-Optica, and if you go into the website of T-Optica, you will find the free, you need only a register account, download calculator, T-Optica calculator. It's directly called like the T-Optic-Calc. Yeah, and you can use it to calculate a lot of things, a lot of useful parameters like pulse spreading and so on in various materials. You able to use some glasses and so on to estimate some femtosecond phenomena, because this company is specialized on the femtosecond radiation. It's maybe one of the main research directions. But it's not only they produce now it's even simpler lasers, continuous phase and so on, but femtosecond optics is one of the main their directions, so you can use this calculator to estimate some phenomena. Okay, so what is important here in femtosecond time scale? We have electron and atoms, and in previous time scales we're going from the macroscopic objects. Yeah, I don't know, it's quite fast going to this image again. We're going to the femtosecond time scale. You can see that in the femtosecond time scale, we have movement already on the electrons. Yeah, maybe in picosecond we have some movement of charge in semiconductors and so on. But it's maybe a bit slower process. But here we are able to consider only movements of the electrons, but atoms already not moved, considered like stable.
Mm-hmm.
So they living in the bit bigger time scale, and that's why terahertz imaging or terahertz spectroscopy very attractive, because a lot of molecules moved exactly oscillating exactly in this period of time.
Mm-hmm.
That's why terahertz spectroscopy is called like fingerprints, because there is a lot of if you have, I don't know, have you or not, good course in solid physics, you will consider various periods of various objects and various oscillations, transitions, various transitions from one time scale, from various transitions of molecular structures and like crystals and so on. So in bigger materials, not bigger, it's like molecular objects usually have vibrational and oscillational types of transitions, yeah, or maybe oscillation.
Mm-hmm.
And exactly these transitions match with terahertz radiation.
Mm-hmm.
With terahertz radiation frequency parameters, so it's possible to obtain some resonances phenomena in this and measure some decreasing the absorption and specific frequencies of terahertz wavelengths, which will be give you information that this material presents inside your mixture, for example, something like that. Okay, going forward again. So we discussed a bit forward. We discussed femtosecond parameters, and now you obtain, I believe, some image how it's distributed, which processes, with example, which what you can study or how why it's useful for various time scales. So now, yeah, this is a final. This is some questions. Yeah, maybe it's not important to discuss right now. I leave it to you for your preparation. You can ask another questions. It's like examples. This is a summary. This is what I required to propose, because usually I don't have time to create this summary in my presentation. I give it to students. Students give some summary. So this summary which is given by students, you can improve it. You can discuss with neural network maybe. But finally, of course, summary is important. So what we studied there. So the bigger the object, the lower the frequency of the moved, frequency, speed of the movement. Yes, and the smaller the object, the frequency is higher. And using this phenomena, we understand the importance of the each specific scale. Yes, and we are able to consider various physics. For example, do you know what is the time of living boson Higgs? Can you suppose, take it information what you just learned?
At a second, maybe. At a second. No.
It's even not at a second.
Maybe
Is
picosecond.
cutting edge of the second. No picosecond. No. You know another how to say приставки.
Prefix.
Prefixes, yes. Mi на пи фем, мили, микро, нано, пика, фемта, атта, зепта, йокта. I'm not remember exactly, but the lifetime of boson Higgs is someone there between yokta and zepta. Sounds very small.
Sounds like.
But it's already nuclear physics and physics. So because how you why I believe that you're able to give this answer, maybe not exactly this is such time scale, but if you remember you know what is CERN. This big synchrotron where what happens? This interaction is not already not in the not the molecules on electrons. It's very fast, or how to say, relativistic particles which interacts and produce not only electrons, but it splits the material, splits the atoms and so on. So it's some how to say, muons, gluons, some subatomic particles, and they of course live in shorter time scale. That's why you should imply that these experiments take it in this period of time, that the living of this boson Higgs should be a bit shorter, because if it will be lived in femtosecond time scales, maybe it will be not required to use such synchrotron-like sources, so powerful and complex.
To find
it could be obtained maybe in our laboratory with femtosecond radiation, but unfortunately no. And the second important things, what I also would like to mention here, that the it was back to our discussion, the oscillation of one wavelength is 1.5 or 3 femtoseconds. That means that if you would like to, invisible range, if you would like to obtain the oscillation of less than femtosecond, yeah, you need to use shorter wavelengths. That means how it's happened how it's technically implemented. The researcher took the setups like titan sapphire femtosecond layer pulses, amplified they to very high power, and obtain a lot of harmonics. But another thing that visible range, you know, we don't perceive ultraviolet because it's absorbed by atmosphere, and like during convolution we not absorb ultraviolet radiation. That means that ultraviolet radiation is not able to propagate in air. Yeah, that means that you need a very powerful vacuum setup facility, I don't know, which will where you will can produce some experiments with higher harmonics, maybe 20s harmonics and so on. You obtain deep ultraviolet, you obtain the pulses which have duration of up to a second duration and so on. And in this case, you will able to study the material of interaction of electrons and so on, and subatomic maybe processes. So it's not already femtosecond optics, it's attosecond technology and so on. So it's beyond of our course, but some information for basics. So it's at least, you know, you should imagine that femtosecond relates to the visible and near infrared, and attoseconds relates to the ultraviolet. And as deeper you're going to the gamma radiation and so on, that's why also you need to relativistic facilities like CERN and so on. Okay, and this was a first question. Usually it's take time. I don't know, do you tire it? Maybe we need to have a split or our classes. Do you need a break, 5 minutes? Or?
We have a break to this later in 15 minutes.
Okay, you have some time when you need to go out. Maybe we can adjust our breaks in the time. If,
Через 3 минуты я побегу.
Okay, so maybe you can. I say it's maybe explain one slide, and maybe later you can break. Okay, why femtosecond optics is important? There are two features of terahertz radiation, because it's very short duration, and it's because it's very high power. I just realized that maybe this lecture is better to explain after this mode locking, because when you obtain the principle why the radiation is femtosecond radiation have very high power, maybe yes, usually, but finally it's like presented like to attract your attention to study, to learn femtosecond optics, because it's have a lot of various applications like that. So you can obtain study nonlinear optical phenomena because of very high power radiation, you have precisely process materials. You can do some medical application like surgery of eyes. Yes, and some scientific radiation like generation, as I just mentioned, it's the generation of X-ray radiation and gamma radiation, higher harmonics. And another interesting and important application is nuclear
thermonuclear.
Okay, you understand me. Due to this, of course, it's better to translate it. The use radiation of shorter duration for diagnostics of ultrafast processes is terahertz generation and using terahertz spectroscopy, because it's one of the terahertz. There is a terahertz gap, so-called term. That's till the end of 20th century, the mankind already reached a lot of ranges of electromagnetic radiation, but in the terahertz frequencies there are till the end of the 20th century there are some problem to obtain high power terahertz sources, and even now the power of terahertz sources may be less than 3 or 5 orders, as if you compare with the other things, and the cost of these sources is very expensive, because maybe there is only one powerful kind of terahertz sources, terahertz free electron lasers. It's located in Novosibirsk, in the Butker University, in the Butker Institute maybe it's called, and it takes like building more than this building, so building more than that, yeah, and they able to fire the paper with that radiation. Yeah. But it's a very just example. So okay, I think maybe break.
Okay, 10 minutes, 15 minutes.
Oh, 10.
Okay.
Я пошел к клинику. Сказал, что 13:10.
И что ты показываешь?
Программа, мне надо выбрать третий, я не знаю. Ничего подскажет и посмотреть, что перекрывает у нас.
Ты не к нам сейчас сюда?
Нет.
Ну, пока.
Скажи, что я немецкую чистоту. Чтобы ему 2 раза не смотреть. Ну, в целом,
Вы не опоздали.
отлично. Вряд ли Дани, если придет.
Знаете, у нас прикол в том, что мы пытаемся Борису подарить подарок, уже хер знает
А, вы еще не подарили?
Нет,
Да, у
потому
него
что всегда
2
кого-то нет.
января день.
Вот всегда кого-то из нашей комнаты нету. Всегда. И...
А
сегодня-
запишите видос от того, кого нет на
Смотрите.
видеосвязи.
Сегодня вроде как Даня должен был прийти. Все рассчитывали, что мы сегодня опоздали, но... Его
Ну,
нет.
слушай, рассчитывай, что Даня придет на пару к 11:40.
Ну, блин, я же к 9 пришел на видосвод.
Понимаю.
На рыбацком.
Как ты вообще на рыбалке? Выбрал рыбацкое, типа, что меньше народу будет?
Во-первых, это, во-вторых, я думал, что там не будет народу, во-вторых, это первое. Второе, он открывал с 9, и третье...
Зеленая ветка.
Зеленая ветка, что
А как ты туда на такси ехал?
Нет,
В метро.
в метро.
Ты в рыбацкое реально приехал.
Где?
Ну, прям, ну подожди, станция метро Рыбацкая.
Я клянусь, что ты же ужаса не был на
Ну,
рыбацком.
давайте.
Примерно время прошло. Так. Okay. Speak English. This is kind of areas of application. So it's not examples direct, but it's chemistry, metrology, optoelectronics, material processing, biomedicine. The latter was responsible for Olga Smolenskaya, but maybe we consider some examples here. I don't know. What is important? We will consider the principle of mode locking, and mode locking it's a very interesting technique which produce due to the some physics, internets of longitudinal modes. It's redistribute the duration, the energy from the pulse, from example in second time scale to femtosecond time scale. So the energy is kept, but it's redistributed from the bigger pulse to short pulse. So the energy absolutely, no, it could be, it's lost, but it's amplified because of we use some pumps and so on. So we obtain the energies which is distributed in femtosecond time scale. And this is analogy with weights. You can see that, for example, this, I don't know how to say it in English. В общем, этот каблук, he is produced very high pressure, yeah, because the small area, he able to produce apply very high force, yeah, very big phase. Because of small area, but it's the same analogy. Here we have very short time scale, and material not able to work with, not able to interact, to give response in short period of time, and so occurs some interesting phenomena like nonlinear optics and so on. But if you redistribute the energy with another period of time, so this process is, the energy is the same, but the processes will be not launched because of it's not so sharp, yeah, not ultra short, not located and not ultra fast direction, dimension. Okay, the analogy, a very interesting analogy with the nuclear or another plant power, yeah, power plant. For example, there is a power plants in Japan. If you take into account our power plants in Japan and compare the power, peak power, it's which is important. It's not power, it's peak power. In the peak power in the, for example, our femtosecond system, it will be comparable. But the difference, of course, because our energy station in Japan produces this power in each femtosecond of time. But this peak power is comparable with this ultra fast, with these power plants, but we have one ultra intensive pulse, and after that we have maybe minus 10 plus minus. In short, this is we have intensive pulse, and after that a long period of time the resonator is absent. So we redistribute all this energy in one short pulses, and after that the resonator is without pulses. So that is the difference. Of course, it's not breaking of energy conservation law, nothing like that, but the peak power is comparable. That means it's a very big impact on the matter in this short period of time. That's, you just imagine what happened. Because it's a 10 in 12 degree is the power which is required to launch some nonlinear processes, optical nonlinear processes. So it's, if you can consider the power plants, it will be like one powerful power plant and so on. And Japan produced maybe 10 plus 14, something like that once. I'm not exactly remember, but it's comparable. I think the highest femtosecond setups now have peak power comparable to all plants in the years, maybe. Yeah. But not peak power in this case. Okay, this is definitions. I'm not sure that it's correct definition that Pn is maximum P at T, because if you take this function and take only maximum, it's not will be peak power. I think the definition should be a bit different. I don't know where the students take it, but the full power and mean power, it's I think it's okay. Okay. So in homework, please work with that. And what is here? Yeah, because of we have very powerful radiation, we consider we're going to that we some phenomena in which is usually neglected in linear optics becomes important. For example, we can define or записать.
Right.
Right, yeah. We can write the polarization like in the Taylor series, make expansion in the Taylor series, and usually in linear optics we take into account on the first term, which is linear, but there is high order terms, and in this case we will take into account the if you have very powerful radiation, maybe the second terms or higher terms becomes also important. That's why we should take into account the phenomena of the second degree, yeah, in higher. And that's why we are going to the basics of nonlinear optics. We will back to this question maybe later. Okay, so this is summary what students do. That's it's the powerful radiation. It's produce a lot of application, something like that. And yeah, now we will consider some important tasks like nuclear synthesis. I think thermonuclear, maybe, yeah.
Thermonuclear.
So the most widespread reaction is deuterium with tritium. So it should produce a lot of energy, and there is two main approaches. The first one is to use tokamak, is quasi-stationary magnetic fields. So and this approach also highly development at the moment, and if I'm not mistaken, in Europe it's planned to produce. It's not the term. How it's called? tokamak, very powerful tokamak, just to start to work and obtain finally this nuclear synthesis. But it's not the aim of our consideration. Our aim is inertial thermonuclear synthesis, which is produced by pulsed femtosecond laser radiations, and maybe the most important facility is National Ignition Facility in USA near to University of Rochester. Previously we have a dense collaboration with University of Rochester, and some researchers come to here and give some lectures, and even in my course about the using, for example, some amplifiers as a sources of this nuclear thermonuclear synthesis. And it's a direct drive and non-direct drive, it's terms which is used for how to work that direct drive, and when you try to use directly femtosecond radiation to initiate this reaction, or direct drive when you transfer energy to the particles, and these particles are already trying to do with something with this cell. This cell is called like hoholarium, I don't know how it's better to translate. So there is very small things. I can show it in this slide. You can see that there is very small things. It's, for example, capsule fill tube is diameter of only 10 micrometers, very small. Yeah, and here it's 5 millimeters, and this capsule tube is this one, very small, 10 micrometers. So there is some cylindrical like waveguide, maybe you can say, and a lot of 192 beams distributed, how to say, подводятся, directed on this waveguide from both sides, and of course a lot of amplifiers and femtosecond laser systems synchronized, and all pulses should be synchronized carefully, and these pulses reflect from these how to say, mirrored walls. Yes, and finally the energy distributed to this small capsule with deuterium in treaty, and finally the aim of these experiments was to start initiate this reaction. Okay, and what happens? There is a review. It's already not fresh, but I recommend to consider the new one. Maybe in the list of citation of this paper you can find another review. But this review states at least the main experiments which have done in this period of time. And what researchers try to do? There are a lot of parameters. For example, velocity of first shock wave, foot laser power, peak laser power. There is two to three-dimensional quantities like asymmetry of this laser power balance between all these beams, like perturbation and so on, which take into account. Finally, all these geometries and parameters reach the only 4 main parameters, which is velocity, adiabatic parameters, and shape and mix. I don't know what is the mix, maybe a mixture of these inside gases, but finally it's going to the temperature and parameter, which also related with the velocity, like energy and so on, and finally it's converted to the efficiency of the thermonuclear reaction. So when the efficiency was higher than 1, the reaction will be started. You can see. So there is another thing that it's like some indirect and direct drive approaches, how to do this, and you can see this energy in kilo electron volts, and this is pressure. So it's the main idea to create a very high pressure, yes, with high energy, and in this case the two components will be able to interact because of the some how to say physical laws since not притягивать, attracted, not attracted, отталкивается, наоборот. No, but I think you understand me. That,
In Russian we will understand.
yeah. Sorry, it's a bit specific term.
It's okay.
I'm not remembering it all whole time. And finally, this diagram reflects some approaches which have on these dates. Maybe now there is some progress again. And here it could be stated that even 4 years ago, the thermonuclear reaction already was fired. Yeah, yes, probably. And there is maybe its yield measured in kilojoules. It's not like efficiency, but you can understood that your energy of spent and energy of you obtained finally should be higher. Yes, in this. So you can see that there is some experiments. I don't know what it exactly mean. It's maybe first is a year, is the month and the day, and the experiments, and some yield from compression, some yield of self-heating. So and finally they found very good parameters which provide very powerful yield. But since we don't listen, if they finally solve this problem, every news sources will be inform us that it's like in case of gravitational wave. Finally they catch it, yes, and the Nobel Prize already given for the gravitational waves, but so this non-nuclear synthesis, this problem is not solved. So I think there are a lot of much more problems regarding this one. But finally, this review claims that they solved at least one of the important problems. They found very good configuration for this thermonuclear synthesis. Okay, so this is some questions. I again spend it to you for working. And now is a summary, also miss it, and another application. Maybe I planning to give you another lecture about mode locking, so maybe we will just go fast through the applications, and you can maybe elaborate more on these parts, especially in your homework, like individual project. So femtochemistry was awarded by Nobel Prize in 23 years ago. So it's the laureate is Ahmed Ziveil, and because it's chemistry, we don't able to read it, for example, in Russian. But there is Nobel lecturers, of course. Each Nobel lecture is published on the Nobel Committee website somewhere, so you can. I think it's clickable. Maybe in the beginning version it was clickable at least. So you can, using this title, you can find this lecture and try to going deep in what he doing. But finally, I could summarize that he do pump prop experiments, and it was maybe 20 years before 20 years before this date of Nobel Prize winning, when the femtosecond lasers only start to appear. Maybe he started even with picosecond lasers, yes, and here he initiated by very intensive pulse the reaction, and the probe pulse measure what happened with the system, and knowing knowledge about the chemistry, he understands the new knowledge. First of all, maybe in the beginning of the 20th century, there was another Nobel Prize laureate, Svante Arrhenius called his name, who thinks that chemistry reactions appears instantly, absolutely instantly. But finally, Ahmed Ziveil and maybe some researchers before him show that the reaction have a specific period of time, and when you know at which time what happened exactly with in chemistry terms with this reaction, you're able to manage it. Yes. So first task is to to measure. The second task is to manage. So maybe you can add some additional components or something like that and insert optical irradiation in specific moments of time, and reaction will be changed a bit different, and finally you can obtain the new materials, new drugs, and so on. So it's a main idea, but I think it's better to add some examples and details exactly in this femtochemistry. This is one of the examples here, but the image is not good, so you can improve it. And this is slide, you can see pulse. This is molecular beam with moleculars, which is studied, interacted in chemical ways, and there is clocking pulse or pump pulse and probe pulse, which is shifted by delay line, and even when each pulse is coming here, you launch some reaction, again, I forgot this word, возбуждение.
Excitation.
Yeah. Some excitation is launched, some excitation, and the probe pumps read the specific conditions. So because of this beam, each new pulses interact with new chemistry components. So we able to measure very good, how to say, reproducible time scale. So in femtosecond, or maybe started with picosecond time scale, you will be able to measure this curve, and maybe you will learn which reaction faster, which reaction not so fast. So, okay, there is a technique for management of chemical reaction. You can see this optical optical impact, maybe on the to not create static monomolecular reaction. It's optical interaction with surface of potential energy. It's using dynamics of non-diabatic perihods, transition, sorry, orientation of this molecule. So because there is a special location now, it's a lot of, like, for example, using vortex radiation, you can use chiral properties of this reaction, and there is an interesting feature about chirality. It's as kind of the subdivision maybe, and it's coherent dynamics or something like that. But also you can decrypt what is all of this term means. And femtochemistry is the definitions. I think we can switch on the next application. It's frequency comps, known in English. It's also very important things which are necessary for researchers to develop new tools. For example, maybe you know that system like GPS and GLONASS required correction which is based on the constant relativity theory. So it's not like very lower time scale processes. So they correct, for example, the management of this Sputnik satellites. Yeah. So something like that. And in this case, there were a big problem that it's impossible to match. For example, there is optical standards, like in metrology. You know, there is etalon of length, etalon of seconds, and there is some frequency, laser frequency, which working like etalons. But another, for example, this frequency is not matched with radio frequencies, so there is a lot of gaps. And this was quite big problem which required to be solved. And what the researchers do, you can say that some text, and they use the main idea was to use supercontinuum radiation, because you know it's coherent. First of all, maybe you have, or maybe not yet, but you have virtual laboratory works about spectral supercontinuum generation. Maybe you will.
It's fourth
course.
I don't know which is fourth. When we developed it, it was 6 maybe, I don't know. But which is laboratory works you have now, it's Maxim decide. So it's there is some property, and finally you obtain coherent broadband radiation, which coherence because there is spatial coherence, temporal coherence, and there is kind of coherence like from pulse to pulse. And here, that means that all these components equal specifically defined phase, yes, one to each other, and this phase coherent one to another one, in one pulse to another pulse, because the process is absolutely repeatable. Management, it's possible to manage it, all details, all parameters, so, but there are a lot of small processes which still not clear it. Maybe you can optimize some configuration, but finally there is a very good stable supercontinuum-like sources. Now we have commercial lasers which we can buy, and so you can produce some supercontinuum light sources and use, if you start to interact broadband light sources, one broadband light sources, or maybe one broadband pulses with another broadband pulses, you obtain it interference which will produce frequencies, specific frequencies, selected frequencies in spectrum, and in time also you will have specific peaks of this radiation. That means you can use it for create a stable technology, and you can match one frequency which is like working like etalon, taken into account as etalon to another one, and finally you have some applications which require very precise measurement of frequency in specific frequencies, yeah, and now you're able to match it, for example, for cesium or another very precise process, which clear without additional maybe additional oscillation or like noise. Yeah? Okay, so this one problem, and another problem, another application which was solved with femtosecond lasers. We're going, you can see a lot of Nobel Prize related to femtosecond optics. In fact, that's amazing. So it's very rich things. By the way, if you're interested, if you really have time and interested, I record, but only not in video, on audio. I listened to Nobel Prize, at least of 2 Nobel Prize laureates in the September, and I have recording and photos of some slides of it was I forgot his last name, who obtained the Nobel Prize 2 years ago, or maybe 3, for stretching and compression. Donna Strickland and Gerald Morovia. It was one of these guys who gives a lecture, so it's quite good because they he also described some time scales, and what it was interesting for me because finally he shows the similar slides like I show you about time scales and relation with these sizes and in time scales. Yeah, so it's basic things. It's good.
Where did you listen his?
It was ICO. It's Optical Optical Commission of Optics. There is such like bureau in optics in Europe, and ICO, International Commission of Optics. It's not only in Europe, but Europe will have a greater impact. A lot of Dutch and German scientists and so on take into account. And this last year it was located in Dresden, and 4 Nobel laureates come to here, give a lectures. It was very interesting, and it was at least one is about measuring gravitation waves, another one about Gerald Moreau about femtosecond optics. The third one was about the how to say STEAT and soul microscopy, and also Nobel laureates who invented. The last one I'm not remembering, maybe it was not in physics, but also interesting. It's not related to this course, maybe later I can check if you know. Okay, and now let's switch to the another Nobel Prize. So it's laser cooling, and like I already forgot how it's called.
Trapping.
Trapping, yeah, laser trapping. So it's there is two Nobel Prize even there. The first one in the laser cooling, and the another one 2 years, maybe 3 or 4 years later, it was Wolfgang Ketterle, I don't know it's included there, maybe not, about atomic laser. It's also a Nobel Prize. It also related, based on the results on this work. So Stephen Chu, Cohen Tanunji, how to pronounce in English, and William Phillips obtained the Nobel Prize for the development of laser cooling and with helps of laser radiation. So again, what is interesting, the first pioneering works was produced in Soviet Union. So you can see Letokhov, Ovchinnikov, Sidorov consider this task. So there is atoms, and you can see that in the temperature room, the speed of atom in the air, for example, in molecules and atoms, particles in 400 kilometers per hour. So it's very fast. So we speak in there, but you listen my voice because of molecules interact with speed of sound. But if you consider some atomic concentrate and so on, special tube, the speed of atom will be like that. Yeah, so it's very fast. If we reduce this speed is caused by Brownian heating. Brownian heating is because they have a lot of energy. That's why they flying in the space. Yeah, like billiard balls. And interacts and changes their energies going inside. So this nature of voice. Yeah, and finally, when you reduce the temperature from only even 3 Kelvin, the speed of was 400 kilometers per hour. So it's very hard. Do you remember speed of sound? 600 kilometers.
300 meters per second.
It's you can convert it, but it's very big. Yeah, but if you reduce the time of your atomic concentrate, if you reduce the temperature of micro Kelvin, you will obtain the speed of atoms 1 kilometer per hour. It's less than pedestrian. Yeah, so that means 1 kilometer per hour. It also looks very unstable. Yeah, but not forget we just in detail considered the frequency time scales what researcher can do. So if you use some cameras, electronic devices, yeah, you will working. For example, all electronic devices are able to work with nanoseconds, some microseconds. So that means 1 kilometer per hour. It's enough to catch some atoms in the even field of view of your microscopes and connect some, extract some information of laser and so on, radiation which interact with this atom and obtain a lot of new knowledges. So it's very interesting idea to freeze that, not to freeze, but it's like reduce the motion, speed of motion of the atoms to able to investigate them. So this is evolution of the experiments. The first one is like special prism based on total internal reflection. So it's a surface because of total internal reflection of laser light. It's interact only with the surface, yeah, and atoms which is fall onto this surface change the energies. And the basic idea that you have there is a resonance lines of the atoms, and you able to usually there are several of them, and you able to use your laser radiation with a bit different frequency. You know what is the Doppler effect?
Shift.
Yeah, shift. That means that you, because of Doppler effect, atom is very fast, it's moving. So if you will add this shift in your laser radiation, the atom, in one case it could be accelerated, in another case it could be deaccelerated. So you can reduce his speed by adding specific shift. And here it's written, so you can see there is effect Doppler. So they absorb the photon, and because of their internal there is some physics which define that, for example, relaxation time and so on. So first of all, you can transform or excite. Transform your atom in excitement state, and after several times it should be launch these photons back, to going to the basic states or ground state and so on. Yes, and if you because of speed, you can he can absorb this energy, but re-excitate these photons with a bit different frequency. And finally, because of conservation law in physics, the energy of the atoms should be decreased. This is a process, and it's able to, because of this interaction, produce very fast. Maybe, I don't know. I read this paper, but I maybe already not remember all details, but quite fast it appeared, maybe seconds, appeared some how the authors describe in their Nobel lectures. So in some position of time, they will found that there is a bright spot of the particles which is anymore not moved in the full volume. So they decrease it and became concentrated in one space of time, or space of area, how to say, spatial dimension. Yeah, spatial area. Okay. Yes, and one question is how to use it. The basic idea, finally, you can see prism. After that, something like that. That atom like jumping on this device. And after that, it's like special, like I don't know, pocket for this atom. But it's not efficient. But at the time, it was, you can see decreasing from 0.0. It's 100. Sorry. Oh, I forgot how to say it. 0.1 seconds and less. But finally, because you need to decrease the speed drastically, what was proposed? Use 3 beams, maybe six beams, which is located in all 3-dimensional, in 2 ways on physical our 3-dimensional space. Yeah, because you can see any vector in 3-dimensional space has 3 projections. So if you create 6 beams which will be interact with atoms in any direction which atoms would like to move, there is 3 projections of these laser beams which will be interact. So finally it was like trapped. Its energy will be decreased. Okay, but this is only one problem, because atom is not photons. Photons don't have a mass, but atoms have a mass. It's the main difference. And so there is a gravitational field which is impact on this. So it's also problem should be solved, and they solve it later. His magnetic trap, which is how to say, not able to work with, not able to compensate this force of attraction, gravitational force. Yeah. So I'm not know a lot of details how it's working, because usually it's magnetics trap. That means that atoms should be not magnetically neutral. Yeah, so I'm not familiar with all of these details. Maybe you can find out and add something interesting to there. But finally, this is the Zeeman effect, which divide. There is a fine structure of the how to say, fine structure of optical, тонкая структура этих оптических переходов.
Optical transitions.
Yeah.
Probably thin structure.
Huh?
Probably thin structure of optical transitions.
Yeah, something like that. So there is some basics with related with effect Zeeman, and this is about some new things that students ask. I'm not ready to maybe comment it right now. It's another geometry, so you can read and maybe try to comment on that and maybe add something new. And so there is interesting things that atomic traps and appearing of the frequency constant, because we just considered this question. And what else? Here it's not included. Maybe it's on the time clock. Not time clock, atomic clock. But now here I would like to say about the next Nobel Prize. It's what Wolfgang Ketterle about the laser, atomic laser. Because the first track, the first task was to solve the to freeze the atoms. The second task is, you know, there is Fermi-Dirac statistics and Bose-Einstein.
Yeah.
You know the difference between them?
Yeah, one statistic for fermions, so for particles with spin, with not with spin drawback, fraction spin, yeah. And for Bose-Einstein statistic for particles with whole spin, one or zero spin.
Yeah, what in this regard principle of prohibition of Pauli, I don't know, запрет Паули.
So there can't be more than one. So we can't place two particles with the same spin on the energetic level.
It's only in statistics of Bose-Einstein, yeah, this is spin. But fermions are able to, if I'm not mistaken, not so.
I guess Fermi-Dirac for electrons,
Yeah.
and they can't place with the same spin, but for bosons in Bose-Einstein statistics,
Like is bosons.
Yeah.
Because they able to accumulate it, they are able to accumulate it and irradiate it in one state, another state. The principle of lasing is based on exactly on that you're able to accumulate a lot of atoms, not atoms, photons in the excited state, and after that they can be synchronously irradiated to another state, and you obtain coherent radiation. So it's a statistical Bose-Einstein. And fermions it's not possible. But another examples of bosons. Another examples is the atoms. Atoms it's not like electrons. It could be accumulated, but it's physically difficult to obtain a lot of atoms with ground state because of what? Do you know? Can you guess? Because of what difficult to accumulate all atoms in the ground state? What is the ground state?
With the minimum energy.
With the minimum energy. What does it minimum energy? We just discussed it.
What does it in?
Which maybe properties follows that your atoms have minimal energy? How it's will be? Could you say something else about atoms which have the minimal energy? We just discussed.
They cannot irradiate.
They cannot
energy
irradiate.
connect with the temperature, and not every. We can't say that all atoms that we have exist in the ground state because of temperature
Distribution.
Yeah, temperature distribution.
Yeah, so that means if we cool, we will cool our atoms in the ground states, they will be, first of all, they will be coherent. Yeah, so there is so terms like de Broglie waves, and the, I don't know, it's also related with the temperature. When you decrease the temperature, the radius of this coherence increases because all atoms inside of this temperature could be considered like in one at the same state. So because of temperature, it could be decoherent, I don't know. So but they could be obtained in one state, and after that you get irradiate. If you first of all you can cool your atoms. After that, when your atoms are cooled, you can excite them in the second layer and obtain transition with irradiation, with coherent radiation. And so this is exactly what did Wolfgang Ketterle. He cooled the atoms as already developed techniques. Of course, he do it a bit later after this Stephen Chu and this researcher, but it's one of the first who did it, and now I think such experiment could be maybe become easier because a lot of progress in this field too. But finally he obtained Bose-Einstein condensate. It's the first part of what he's developed, and the second one he demonstrates that it's worked like a laser, really, because it's the same magnetic traps, but what they did, there is a group of atoms in the air which not fall on the ground because of magnetic traps in some period of time, but they cooled in ground states already. So he a bit improved the techniques to cool the atoms finally to ground truth. And the second one, it's necessary to demonstrate that it work like laser. How we do it? This is looks quite stable field of atoms, area of atoms. He switch off the this magnetic trap, and atom fall down because of attracting by Earth's gravitational field. In this case, he performed double slit experiments. So if it's coherent atoms, they able work like laser. So they directed because of attractive gravitational field going in this direction, and he gives some slits, and atoms going from the slits like coherent radiation produce interference fringes. So it's demonstrated like a very beautiful experiment. He measures the phase and amplitude of these atoms, and it's really demonstrates. So because previously you see the atoms, it's how you can check that it happens. Of course, you need to perform the experiment. So this demonstration really very beautiful. Give us insight that the atoms are coherent and able to interfere because they are in the ground truth, and it's coherent absolutely. So after that, it's opened a lot of applications, but the Einstein condensates, I don't know, able to solve a lot of problems, but maybe this presentation not included, but maybe my previous one is included maybe. But it's all taken from Wolfgang Ketterle Nobel lecture. There is such journal, Physics Успехи in English. In Russian it's Успехи физических наук. And here you can, every year they publish a lecture, already maybe 100 years. They translate of the lectures of Nobel prizes and publish it in this journal. So you can read it even in Russian. Very big lecture, and very interesting to read all of this what we consider in these Nobel lectures. Unfortunately, it's not only there is a similar journal, Chemistry Успехи, something like that, but it's not do that like Physics Успехи. Okay, so that's why Ahmed Ziveev lecture is not included. Okay, in the last one, maybe we're going to the frequency combs, and it's kind of application is atomic fountain of Zacharias-Chu, which is to measure the gravitational rate shift. It's also important things about gravitational phase shift and understanding what happens with the black holes and so on, if you're not mistaken. Okay, what is this? This is you can see this is a trap, laser trap, and finally they try to how to say подбрасывать, throw up, yeah, I think throw up this field of atoms, and you can see there is a high frequency waveguide which impact on this atomic cloud maybe, yeah, and there is some changing interaction with this high frequency electromagnetic fields with these atoms, so it's like which demonstrates a great shift, this gravitational great shift. So also important experiments. And the last one, what we consider is the atomic clock. So you can see these slides. It's like progress of the measurement of frequency, and you can see this is preciseness. This is a 10 minus 5, and this is a 10 minus 19, 18. So a lot of orders of magnitude, and you can see before the when the laser was invented, it was 10 minus 5, like microsecond, yeah, starting from Q-switching, which was pulsed laser. First laser was pulsed, and it was in Q-switching mode, and the duration was microsecond. After 2 maybe years, they going to nanosecond and picosecond later, as you can see. But finally, it's became clear that if you considering the transition in pure, how to say cesium, what is it?
Cesium.
No. I mean not only cesium, various like gallium and so on. There is some transitions, some
щелочные металлы.
some elements. Okay, in some elements transition in pure some elements, so it could be more precise the frequency oscillation, because it's pure mixture of these elements, and it's not contains any contaminants which can shift and add some errors. So in this case, that's why the etalon now of second is related with cesium some oscillation, and you can see it's exactly what happens there, and some progress reflects of this field. So it's application of optical frequency comps again. So this broadband radiation interacts specific with resonant frequency of the specific elements. Yeah, that's why we obtain the able to measure exactly second and so on. It some slides demonstrate how it works. So there is chambers, there is some magnets and detector, how it's cesium atoms higher energy states and lower energy states. So you select these oscillations, and how you can use principle. You can create an atomic clock. Yeah. Okay. And finally, this is, I don't know, example. There is even on the hands already. I didn't know it. It's like students' homework, so you can read in detail about it. So there is an oscillation of frequency comp. You can say there are a lot of oscillation where you need to exactly measure the synchronization of various laser pulses. So telecommunications, optical telecommunication with satellites, satellite systems, and so on. And again, if you consider the task of thermonuclear synthesis, you have a lot of lasers. You need very precisely synchronize them, and synchronization 10 minus 50 or not, maybe not enough. So you need very precisely synchronize. Again, at the second radiation, when you're going from the bigger wavelengths, yeah, to the shorter wavelengths. If you draw big wavelengths and shorter wavelengths, which is located exactly in some position of the oscillation curve of the laser with how to say, seed radiation, which is rise this high frequency harmonics. You have some mismatching, phase jittering, and so on. So this question also should be solved, and going using supercontinuum with this high frequency comp is also very necessary for that. Something like that. Okay, so I think that's all for this lecture. So there is some summaries, some questions, and I give you this what we not consider for you, for your consideration and improvement, one of you. So please define who will be, I maybe today try to solve, to send you the list of the questions which we would like to cover, yeah, and you maybe will distribute yourself with various who will be responsible for each topic. Okay, and finally let's consider the second tasks. Oh, maybe it's there, yeah. About mode locking, code switching is the most important things that I would like, if you forgot everything about the course, that you remember what is mode logging and what is code switching and what's the difference. So usually it's clearly very often claiming that students remember maybe 1% from their considered in the classes. So maybe I think that I would like that you remember this one. This one, because it's all basics of femtosecond optics. Okay, which is slideshow here. Okay, and what we would like to consider, maybe we will not enough time to consider everything, but maybe I don't know. If you have time, maybe we can go back and give you maybe we will short earlier in the next lecture, and you will have a bit more constant period of time accumulated in one period that to prepare your own presentation and so on. So maybe it will be convenient. It's up to you. So if you're tired, you can stay me when the time. If you're not, I will continue. Maybe.
It is okay, I guess.
Okay.
Yeah.
Okay, but maybe it will be. It's not so interesting like previous one, but because I think previous one is a lot of application of your prices, and it's quite easier to see and relaxing. But now it's a bit more specific. But it's also only I try to not include a lot of equations, but try to reflect physical principles. Because in Russian I teach exactly a practical part. Because Professor Kozlov gives you theory. Not you, but Russian students. But here, this theory was previously maybe not that theory. It was given by Rostislav Arkhipov, but now I have a practical consideration. But maybe it's okay for you. It will be practical if you have the second optics. Okay. So I already speak about progress of femtosecond optics in time, and you compare. Now in this slide you can compare it with electronics. You can see that the electronics is much more limited. And could you explain the first my question to you? Why? Could you explain this curve? Why it's limited there and why it's limited there? And what is this jump means? So three questions.
They're limited because of speed, I guess. Speed of electron is much less than speed of light.
Yeah, we just discussed it. In the previous lecture. That is even picosecond scale. You can see picosecond scale, and there is a saturation. Yes, so it's in the next.
The next question was about...
what here, or why it's also saturated here in the end of the femtoseconds?
Because of speed of light also has a limit.
No, not speed of light. In this case, why this is a next acceleration there? But we just discussed it in the previous lecture. I told you, I asked you special questions.
About sizes, about boson fix?
No. No, not boson Higgs. Before the break. It was so.
Maybe because of special fundamental quantum limit connected with the size of something.
No. Okay. What is
It's
the
with
optics?
period.
Do you
period
know?
of,
Maybe
pulse.
some of you planning to be in the PhD studying and postgraduate studying, and you would like to obtain the PhD degree on optics.
Uh-huh.
Do you know what optics means? Which
Range,
range,
Optical
frequency
range,
range is
yeah.
covered?
visible and infrared, near infrared, and near ultraviolet.
Near ultraviolet. And what they found, why you can see this is a very big progress in the beginning, but later even more and more complex became to obtain the shorter optical pulses. Why it's difficult?
Because of the wavelength limited?
Yes.
Limits?
Yeah, we just discussed it.
Yeah.
1 femtosecond it's less than one energy, one oscillation of electromagnetic femtosecond pulse in the visible range, but not in the at the second optics, which use higher harmonics of X-ray, far ultraviolet, and so on. So that's why the answers on the first question immediately appear from here. That at the physics, it's already not an optics. It was first experiments was published in this century already, and the attoseconds range now working in the vacuum with not radiation with visible range. So near infrared radiation only used as a source of these high harmonics, and later it's converted to higher harmonics, and already these harmonics produce at the second pulses.
Mm-hmm.
So that's the thing that you need to understood. That that's why what's the next important consequences we can do that. You know, Moore's law.
Yeah.
Yeah.
Закон
And
Moore's.
what happens? What problems with this law right now?
It is about
It is
data.
violated now.
It's violated in some wording, but why?
Because of
Because of
the
the
finite
size
sizes.
problem.
Yeah,
Size
because
of transistors.
Transistor size, yeah.
yeah, transistor size, thickness, and it's not. It's already one layer of materials of semiconductor materials. It's quite difficult to create such optical, not optical, such processors. Very thin. It's multi-layered. It's in general. It's there is. It's not a Moore law. There is such man who consider it very globally. It's technical director of Google, Ray Kurzweil. He is maybe, it was technical director of Google. I don't know now what is now with him, but he considered everything like Moore law only as a part of global evolution from the first amoeba, I don't know, to the mankind. He everything of that is like calculation in time. So it's our evolution process. He drawing very good exponential curve, how it's increased, and he predicted that the calculation. First of all, he predicted in the previous century that the computers will be much powerful than people, and he even predicted maybe in the precision of the 1 year that the best chess Grossmeister will lose the computer to the chess, then maybe go again. Yeah, the game. And now because of appearance of GPT-3, I starting to refresh, because in another discipline I taught the students about this Moore law. I spoke that this guy predicts that maybe in the 2020 the power of computers will be consider it with like one human brain. And the end of this century, the end of this decade, it will be comparable, the power of computer comparable with one computer will be comparable with power of our mankind on the world. So in some way he predicts artificial intelligence, so on. But GPT-3 is a very good example of that, because it's not predicted directly in how it will be. You know, there is another Nobel laureate, Roger Penrose, who wrote a big book why it's artificial intelligence is impossible. It is also valuable scientific researcher who thinks that it's not possible, but finally I think there is a compromise. Sounds like neural network can do something, but the idea was that it will be the human will be direct and managed, like your smartphone help you to work faster and maybe navigate the car faster and so on. So it will be held seriously, but maybe it will be not like fluent artificial intelligence. But maybe it will be, I don't know, it's very Nobel Prize consideration. It's maybe, I'm not fully competent on that, but interesting that it impacts on this photonics and femtosecond optics, because the computing now, electronic computing is limited, it's one-dimensional because you need wires. Yeah, the light is two-dimensional, which is the first important thing. The second important thing that optics, it's second order of degree faster than electronics. So finally you obtain a lot of place where you can obtain keeping this informational law forward. So it's not Moore law exactly, but it's called. There is a lot of such laws demonstrated in other things. For example, there is a law of direct price, which is, if I'm not mistaken, it was the price over the time of LED. So it's also decreased in the maybe even 10 years, it decreased in one order, something like that. There is the same price in informational theory, like the number of scientific journals also increased like exponentially, starting from the first journal 4 centuries ago, and now it's increased like an exponential curve. And even the population of human at the maybe even 50 years ago considered that it also could be exponentially growth, but finally it's going to the so-called S-curve. So it's not possible to feed a lot of people on the small years. So that's why it's like another problem, like it's this S-curve cloned like logistical curve. When you have army, you need to move some supplies for this army, and if your army going to war with a broad area, you have a lot of problems to supply them, to feed your fighters, and that's why it's not possible to expand absolutely. So finally it will be
saturation.
Yeah, it will be saturated. So it's like the same things going with population of the earth, but it's no like not like I think right now it's not like an optics and photonics. And by the way, in this case, if you start to think about it, do you think if any absolutely, you know that how is Moore's law is now violated? It's because of number of kernels, yeah, cores which used and so on. You use not flat or volumetric things. They will use optics. There is a physical limit. If you extrapolate Moore's law, is there any physical limits to where it should be stopped?
If I'm not mistaken, Moore's law is violated because of quantum size effects that are.
But we consider it. I just giving Stuart not speaking about violating. Quantum size effects is important. I speak. It's still will be valid. It's not a pure Moore law, but it's like informational development and so on. Informational society and so on, and maybe how long could be extrapolated further. how much orders of magnitude we have in physics. You know, in physics, what you know some physics constants.
Constants.
Physical constants like Avogadro number, like
Planck
Planck
constant.
length. Yeah, if you consider Planck
10
length.
to the minus 13 and
Yeah. So the length, the smallest length which we know is the Planck length, and it's still we now with this nanometer scale we still far from Planck length. Yeah. So that means that if you will find technology, it could be optics, I don't know, femtochemistry, maybe yocta chemistry or photonics or photonics already. Some new techniques which, for example, Ray Kurzweil considers that he thinks that like nanotechnology, he predicts that it will be femtotechnology, so we will able to work in the, if we will survive, of course, we will able to operate with small numbers, small elements like in femto, like I don't know, muons, gluons, and so on. So to create some computing device in this subatomic scale. So he predicted, and maybe after the 20 years approximately. Okay, and so the my general question: if there is a paper in Science on the topics, I just speak about that because of this paper. In this paper, it was considered that there is a fundamental, if you take into account physical constants like Planck length, speed of light, and so on, how many orders do we have that to approach to these constants, not possible to create the most powerful I don't know, computer. And finally, it was like it's not the paper like I don't know, Einstein relativity works with a lot of equation. It's like a rather discussion. So he considers that the most powerful computing process is nuclear reaction, so like nuclear explosive. So it's operates with it's really, if you consider in these terms, it operates with subatomic particles. Yes, like synthesis, thermonuclear reaction. Yeah. So that means we have he just considers these processes and extrapolate the speed of what we speed of invention of covering our new ranges of computation with this time, which give us these limital constants. And the consequences of this summary of this paper that we have approximately 1 century, maybe 1 century with half. So if we will consider, we'll keep this speed of constant of invention of these new devices, finally we will approach to this physical constant what we have now, what we know now. Maybe when we cover to how to say zepta physics, it will be another knowledge about universe, and we can be shifted. But I think first of all we should survive for that. Because of a lot of treatments in the world. So I think it's a very interesting topic, and it was glad for me that photonics takes a very important role right now in here, so femtosecond optics, because usually, of course, it's very important to be IT specialist, but to be a specialist in photonics also very relevant profession, I think, because it's you will know you can be cover the best I don't know, technology which produce the best computational devices in the future. So that's why it's a very important thing. Okay, there are a lot of works about performance, and this is do you have 2 study guides in Russia about femtosecond optics and femtosecond technology, and these study guides includes some like history of the development of femtosecond lasers, and you can see it started from microseconds. First Maimons lasers was, as I already told, in microsecond pulsed laser. Then 2 years nanosecond, and you can see less than decade its approach to picoseconds. That means it clearly reflects this high progress here, because it's very simple processes, and new invention give you new a lot of shortage of the pulse duration. But later there are a lot of more complex phenomena should be taken into account, and you can see the first we started from Q-switch, we should consider it in this lecture, and later we going to the mode locking. You can see where is this passive mode locking, active mode locking. So you can see that the passive is like more good in terms of shorter pulse duration. Then you can see that you have some solving another problem, like for example the second generation of lasers. The first one was in dye or maybe pulsed laser with Q-switch. The second one maybe is dye, so it's with liquids inside the resonator. Yeah, it's very inconvenient, a lot of problems with that liquid. And finally it's going to vibronic crystals, maybe titan sapphire. You can see titan sapphire is here. And another important problem, which is could be reflected in these graphs, you can see that finally when we approach to the femtosecond time scale, we're going to, and you can see how it's decreased the speed of covering new shorter femtosecond ranges here. So it's the problems was dispersion, because any optical elements produce pulse broadening. That was exactly what I said in the beginning of the first lecture, that we were able to obtain. It was demonstrated in this beginning of the 6th century that the duration of 3.5 femtosecond lies radiation in the visible or maybe infrared range. You can see titan sapphire. So it's only one oscillation. It was demonstrated, but it was only specific period of time because of air. Maybe it was in vacuum. I'm not going deep in this initial paper, but if you have air, your pulse will be spread because of dispersion. If you have at least one optical element with transmit the energy, you include dispersion, and also include dispersion perturbation in your pulses. So it's a very difficult task to obtain so short pulses. And finally it's going to at the second range, and now I think even shorter laser pulses will have here. Okay, we should consider some of basic technology which is used here to produce such pulses. The first technology is Q-switch. Let's consider. It's a question, I think it's, we will discuss in your practice of this question. So what is the Q-switch? Q-switch, you know how it's translated in Russian?
Modulation добротности?
Yes, exactly. So it's Q, I don't know, Q, what is Q? Добротность. Yeah, switch is like modulation, but it's not direct translation, like in ghost imaging in Russian, phantom visualization. But switching, so it's like переключение, rather переключение, not modulation. Okay, so what it means? It means that there is, first of all, do you remember three main important principles to create laser?
Population
Inversion.
Population inversion. Okay, now it's important only that principle. The second one is feedback, and the third one is the gain. Now we would like to consider it exactly on the population inversion. So delta n is exactly the number of population difference between layers. Yeah, if it's how it is positive or negative depends on the what is the ground state or this state. So if you have enough population inversion, we will able to, especially in the beginning when the researcher would like to create such lasers, the population inversion was difficult maybe to achieve very efficiently, yeah, and it's was proposed to use like shutters. So you put shutters, and you have a pump inside your media, and you accumulate the population inversion, and after that you open the shutter, and everything collected energy able to work with the second laser conditions, laser generating conditions of feedback. The shutters prevent the feedback, so the excited photons irradiate in various ways, but only one mirrors working, reflected back, but when radiation going in this way, it's blocked by shutter. So you don't have a feedback from here. But when you remove or open the shutter, the radiation start to work with full feedback from both mirrors, and finally you obtain only photons with direction which is located in that in the direction of the location of the mirror. In this case, only these photons is survive. The other photons is also stimulated. It could be created due to spontaneous emissions and so on, but it's not accumulated, not increased, gained maybe because of the absence of feedback. And these mirrors provide such feedback. And in this case, when there is these mirrors, as you know, should be semi-transparent, and the radiation going through it, and you can see that the accumulated inversion population inversion is decreased, and in this case the flux of the photons increased, and after that decreased. That's the essence of Q-switching. So you have in the CV running, continuous wave running of laser, you have power, and everything which is collected directly, part of this going through the half transparent mirror and then radiate, yeah. But in Q-switching mode, you have such oscillation when your shutter is open and shutter is closed. So there is a time when resonator is empty. It's very important. Okay, and we could, if we know principle, as researcher, you can start to do how to implement it in physical device. And how it could be implemented. You can see, you know parameters like amplitude, phase, frequency, polarization, I think it should be. And you know the principle of constructing device. For example, it could be mechanical, rotating mirror, rotating prism, it could be electronics, it could be optics or photoelastics, or you can propose maybe even photonics modulator. So let's consider some of them. So the most the obvious things is amplitude. So shutter usually blocks the amplitude, but for example, you know Pockels cell and so on, the devices which inside have a crossed polarized and cell which based on the Pockels effect, which rotates the polarization during the applied field. So in this case, it's used like polarizing principle and so on. So what happened here? We consider first optomechanical shutters. You can see the first one is the chopper. By the way, do you know how to say chopper in Russian? Correct. Huh? No, nobody knows it usually, but there is a specific word. It's called obturator. Yeah. It's specific physical terms. It's obturator, so you can when you will work with terahertz and we'll discuss it in Russia, you can say obturator. But everyone uses chopper. Okay, but in English it's chopper, so you have chopper, rotating disc with holes, and only at the moment when at this specific, on the way of the laser pulse there is a hole, it's a condition for feedback, and the others we already discussed what happens with simulated photons. And the next one is active element. So we can say, for example, tilting mirror or rotating mirror or rotating prism. So for example, in this case only also specific position when there is a mirror going, so this is inside cavity something, this is one of the cavity mirror. It also could be working like shutter in temporal, if you will consider from the dynamic position. Yeah. And the mirrors could be some inclined somehow, or maybe rotated right now. So you know the speed of light is very fast and the rotation is very slow. So if you consider from the point of view of photons, this rotation of the mirror will be very slow. So a lot of photons can be generated at here, fly back and forward, and maybe several times. So it's not a problem, this physical rotation of the mirror. But when we reach this position parallel to the another mirror, only in this case there are good conditions from feedback, and the laser is created. The same for prism. It's not important what will be. Okay, this is phototropic shutters. There is such case. I don't know what is it exactly. If speaking true, is student added. So there is some effect with dew. Maybe it's phenomenon saturation of okay, it's like a saturative absorber. We will speak about it later in mod locking. So there is, you know, photochrome glasses, for example. When you go into the sun, it becomes darker. So there is some phenomena like phototropic phenomena. I think it's related one to each other. When there is a radiation, because of those of radiation, there is some saturation limitation at first. So it's one of the example is power limiter. For example, when you're working with laser radiation, you need to use glasses to save your eyes. Yeah, but when you're working in eyes, if you take just filters on your glass, yeah, on your eyes, you will not see the beam absolutely. It will be very difficult. So the problem is to create such material which is working with when the radiation very small power, it will be transparent for you. But when the power is increased to those which could damage your eyes, it should be ultra fastly blocked and switched. So it's and there is such devices like saturable absorbers, and for example, there is nonlinear optical property of the material which provides to produce care limiting saturable. It's called power limiters. So it's constant in the first, but if very powerful radiation go through it, it's produced like self-focusing, self-mismatching, and so on. In this case, material blocks the radiation which are going there. Okay, so it's one of the example. I think it's shown something like that, but you could read the example. We just already discussed briefly this one. It's like Pockelis or Kerr effect. So it's you apply the voltage, you have two polarizers, and the polarization of light could be rotated depending on the applied voltage here. Yeah. The next one is magneto-optic shutters. So you can see that you can apply it on magnetic fields based on magneto-optical Faraday effect. Yeah, it's another example. And I already discussed it with you with vanadium dioxide. This examples of these two lattices structure. Yeah, it's in one lattice is absolutely transparent. The another one is work like a mirror, and it's have a very fast switching time, so 100 femtoseconds. So using this dioxide, vanadium dioxide, you can create very fast co-switching lasers. But co-switching, I'm not, unfortunately, I'm not expert in the laser construction system. So what I know from the papers. But sometimes you read the paper, but the authors who work in these fields live beyond the discussion of in the article, the questions which is important. So I don't enable you to talk. I know the co-switching laser still working and still popular, but if we consider the curve what I showed you earlier and progress of obtaining shorter and shorter time scale, co-switching laser is not efficient. I believe it's because of the not only shutters himself, it's rather it rather relates to the spectral width of the, because you know the shorter radiation could be produced, then the broader you have the initial spectrum. So if you're working with not effective active media which not support a lot of transition in the broad frequency bands, yeah, it's not possible to create a very short duration length. But if you would like obtain high powerful Q-switch laser for laser processing, it could be picosecond, nanosecond. In laser processing, not necessary to use only femtosecond laser. You can use nanosecond laser too, but sometimes it's not so accurate, but nevertheless, it's easier to produce and maybe. And in this case, Q-switching is important. But in framework of our course, femtosecond technology, obtaining very shorter femtosecond laser, it's not important process. Okay, it's question for you. I miss it, but we will discuss it, I think, later. And we're going to the mode locking. First of all, I should ask you, do you remember what is longitudinal mode and what is transfer mode of electromagnetic radiation? Just tell me that you understand it fully.
Longitudinal продольная,
Yes.
And others поперечная.
Transfer is
Поперечная. So you ask about
what is it? Do you imagine what is it longitudinal mode and what is it transfer mode?
I guess it is defined by direction of electric strength vector, and it is about limitation of modes in resonators, so we can have longitude modes and transversal modes with limited properties there.
You are right, but why are you asking here regarding these slides about it? Yeah, for me it's important discuss to exactly longitudinal modes.
Mm-hmm.
You know, just a bit analogy from how to say it in mechanics, from mechanics. Do you know how to say, I don't know in English, skakалка, jumping rope?
Uh-huh.
Yeah. Do you know what is it? It's like kind of oscillator.
Yeah.
Yeah. You have two edges,
Yeah.
which if you start to how to say rotate your rope, it could be considered like oscillation. And what is important at the edges, you have your ropes should be fixed, so you're unable to obtain oscillation if your ropes will be like that. So to obtain to jumping on these jumping ropes, you need to move your arms synchronously. It was funny for me when I was in school. I was going to the roof, and I have a very long cable to another building, and I just found occasionally such that if I, for example, perform 3 oscillation of this cable, it was not on the voltage. I was so stupid, but I how to say amplify or stimulate this oscillation, 3 oscillation going here and then reflect from this side and going back for me.
Mm-hmm.
So if I continuously oscillate very long time, I am able to obtain the oscillation like that and
Yeah.
obtain stable waves.
Yeah.
Yeah, finally. So it's because of cable very long, it's the frequency what I need to touch this cable was not so high. So it's if you have small like jumping ropes, you need to very fast move your arms to obtain a lot of oscillation. But if you have a very long cable, you're able to obtain a low frequency modes like that. Yeah, I have maybe 200 meters between two buildings, so it's very long. Maybe 200, maybe 100. So it's quite long. So it was funny, and I observed all these modes. And what's interesting is that if even you start to oscillate in one mode, it could be like that. Another modes could be oscillating like that, but the most important that you need to matching conditions. So at the edge, as you can see, there are everything 0. So if we will find, if I will select frequency of oscillation between that and that, in the middle of that, it will be not obtain standing mode because of some decoherence. Yeah. These modes should be equal. How to say, multiple modes in whole number of modes should be located over your resonator. If it will be not exact, it will be not possible to obtain such a good oscillation. Yeah, that's why there is a specific modes, and in what happens in the resonator because of some effects. There is a, for example, if you have quite big resonator, even several centimeters or millimeters resonator is quite big, comparable to the wavelength, which is nanometer. Yeah, hundreds of nanometers. So here you can find a lot of various modes which could be live inside it due to this condition. So and if we active media support it, yeah, there is transition between each wavelength of inside this resonator. You will obtain you can gain all of this mode inside the resonator. For example, white titan sapphire laser is most important because it supports a lot of modes from 700 to 900 nanometers. He supports the lasing on these frequencies approximately, and in this case, you able to obtain a lot of frequencies, and this is selected by color for simplicity, and you can see this 0 frequency and frequency plus one frequency, another one, and what happens in resonator. You can see if not special condition matched, each frequency can be generated in resonator and I don't know how to say. So it can be died also because of spontaneous emission. So because of spontaneous emission, in some period of time, it's in femtosecond range, some wavelengths should appear here and going in this direction, another one in that. Mirrors define the direction which will be survived, but in general, all frequencies could be generated not synchronously. But there is a special regime which is called mode blocking with all modes of resonator. So we just discussed what is longitudinal modes. Longitudinal modes is just this stable standing wave or maybe moving wave in the resonator with specific frequency. So the longitudinal modes is like the regime of oscillation in the resonator which have a specific discrete frequency. Yeah, it's very teeny, it's less than nanometers wide, and this modes is located could be live in your resonator, and these modes could be matched or could be not matched. So locking is such kind of regime when your modes became matched. How it works? Let's consider from mathematical point of view. We have 2 + 1 modes in resonator. We have we consider what is a match. It means that the phase of each mode is the same. Again, I show you maybe 5 minutes this image, but I didn't ask you what about how the radiation with various wavelengths could be matched. Could you explain?
Can be matched, you mean?
Can be, for example, can interference of 2 different wavelengths coherently interact or interfere?
Maybe only if the wavelengths are very close to each other, but if we have two different wavelengths, they do not interact with that.
No, they interact.
They interact.
Somewhere here, you will see that this, for example, this wavelength is not matched with that wavelength. This is a maximum for that wavelength, but for this wavelength it's a minimum.
Mm-hmm.
It's not able to interfere or interfere destructively.
Mm-hmm.
But here you have some pulse train. It's called in Russian zug of waves, and you can see that these waves are in phase in this period of time, and this is a like coherence time. Maybe it's called. So you have a broadband pulse of waves, and it could be each wave could be shifted arbitrarily. For example, if you have numerical simulation model, you have oscillation like that. You just wrote the program and shift the frequency each of the wave. It could be like shown here, or it could be like drawn here. For example, our wave not in phase, and this wave in phase, also not in phase. Maybe only these two in phase, but this one not in phase, and this was in phase again. So it's in phase or out of phase. You can manage this process. I don't know how it's exactly in one wavelength, so you need special devices, special thinking for about it, but you can manage it. But finally, there is a very specific regime, and to describe it, we just assume initially that all modes in phase initially. In this case, we should create this one mode, another mode, there is a phase difference. Yeah. If they match it, so phase difference should be 0 in one period of time. Yeah. So we could write our pulses as the sum of each modes. Yeah. And there is some if they indifference or if they match it, you can see L and phi. So L is a number of the mode.
Mm-hmm.
So the difference only in the in number here. So it's like one sinusoid. It's like in this example. It's created like in this 4 omega, 5 omega. So but all of them in phase. So it's exactly here. Yeah, you can see this one in that. And if we consider open the brackets from this equation, we will see that this is a geometric progression. And there is a formula from mathematics that there is a geometric progression, the sum of geometric progression, so you can calculate the sum of this progression, and you will see that this equation like that. It's their graph is exactly like that.
Mm-hmm.
So if you summarize all waves in phase, you obtain something like that. That means that in one period of time, all of your waves traveling in resonator in phase, and another period of time so you have small oscillations, and exactly you can see. Let's start to analyze this equation. The period of when, for example, you have a length, resonator length, L, and this length of the resonator should be matched with the number of modes. For example, if we consider 7 modes in our resonator, we obtain two global peaks and 1, 2, 3, 4, 5, maybe 6 minima, maybe I don't know, it's not matched images. So the number of minima should coincide with the number of this standing wave in the resonator. It's not standing, it's like already like traveling. So this pulse train traveling inside resonator back and forth. That's why we have a term 2 here, and speed of light. Maybe it should be divided speed of light in the resonator. So it's not speed of light in air, it's speed of light in the material. Okay, so that's all about mode locking. And what else? It's also important to know that there is a mode which is supported just by length of resonator, and there is as I spoke about titan sapphire laser, there is a special control, maybe envelope, which overlapped with these modes, and only within this peak of this envelope there is a condition for games. So it's like from material science, from the parameters of the electronic transitions which support each materials. That's why titan sapphire is one of the best. It supports a very broad, provides very broad luminescence curve, and luminescence, that means that spontaneous emission able to produce, and after that you can work with the spontaneous emission and retransform it to the mod-locked radiation and the second duration. And the next question, how to do it physically. So we consider the basics, the principle, and now active and passive mode locking.
Can
So
we have a break? or
Okay,
something like
okay.
that?
okay,
Так, у нас всё.
Yeah.
if we can continue.
Because
in
I
the-
think that
Okay,
that's
I
a lot of
it
information
was
for my
exactly
brain.
what I
Yeah.
predicted. That it's not so easier, so it's you
Yeah.
need to follow it. So we can continue, stop it today, right now, absolutely, or we can break and continue. If up to you.
Maybe continue tomorrow.
Tomorrow.
Okay,
Yeah.
let's do tomorrow. Tomorrow at the same time, maybe, yes.
Yes.
Okay,
But I don't know about the presence of this auditorium. It's because you would like to 11, start to 11, yeah?
11:40.
Not,
Maybe
not,
11:40.
not at 7 p.m. So
Okay.
we can
And not at 7
at
a.m.
12.
Okay, let's try to do it in 11,
Mhm.
no problem, but we need to coincide the question about auditorium. I just ask Olga Andreeva and Arkady if it's possible, yes,
Okay.
Okay.
and let you know.
Okay.
Thank you.
And we will do group chat in Telegram.
Yes, just send me a link and it's the most easier way to send
Communicate.
message to everyone.
Okay.
Okay,
Thank
thank
you.
you.
Okay, maybe if you have some questions,
So this is mode locking, especially for pulse generation.
For generating short pulses.
it's
There is a
we
name.
just discussing the two main techniques, which is allow us to produce ultra short radiation, ultra fast, ultra short duration.
So, and the larger number of modes our resonator is supporting, the shorter pulses we get.
Yes,
Okay.
it's exactly. If you have a wider envelope, a wider number of modes should be in phase, and that means you can see that this is a duration. Yeah. And if you have very small resonator and this envelope could be neglected for example, very teeny thin resonator, it support only 7 modes, so the thickness of this
Will be larger.
pulse train will be only 1 divided by delta nu generated. So it's yeah. But if we increase the number of modes, the thickness will be decreased because of it should be like follow the equation of mathematical geometric progression. So in this case we obtain shorter and shorter duration, and inside it we could draw a laser oscillation of like sinusoidal wave. Yes. So it's, of course there are a lot of modes, but finally a lot of modes should be in phase within this. It's also envelope for each mode.
Yeah.
It's going back to this image. Yeah. You see that this is part of the. If you have here is quite a lot of modes. If you decrease it number of modes, you will increase the width of this radian.
But
Time scale.
but the frequency of all these modes are very close to each other.
Yes.
So that is why they interact with each other. I mean, for example, we in fibers we can in fibers we provide different signals for different users on different wavelengths, and we don't care about their interaction because there are no interaction, but their wavelengths are quite different. But in this case, we have an example when waves with different wavelengths interacts with each other.
I believe when you speak about mode locking in fiber, it's also possible. In one of the next generation of the laser, there are erbium fiber laser. and so on, which use active medium like terbium, and there is ring resonator inside. So the principle should be the same.
So it happens because of mode locking. If there was no confinement for our modes, there will be no interaction between that.
But of course, if you have one mode should you have the same polarization, and modes have orthogonal polarization, they will not interfere. Yeah, it will be considered like separate sources. But I believe usually it's how to say, generated inside this resonator. That's why it has the same polarization. Because of the basics of the stimulated radiation. What is stimulated radiation? It's the same radiation with the same frequency, but frequency could be a bit different, but the same polarization, because one radiation with one polarization stimulate new radiation with the same polarization. That's why. But because of some layers, could be a bit different frequency.
But when we generate continuously radiation in the same resonator, we also have resonator where we also have some kind of mode locking, and there are also, as I understand, different modes when we want to generate not pulse impulse pulse radiation but continuously radiation, and in that case what happens with these different modes? So in this case they interact with each other and we obtain pulses, but
they interact not immediately. You need to create conditions. They started to interact, and this is exactly what I would like to show you here, but in the tomorrow. So there is special condition how you can stimulate this interaction. But if you doesn't care about it, even this femtosecond system where you have laboratory works, we are working not in femtosecond mode. For example, there is a Kerr lens effect, mode locking, which is necessary to push the button to make some some vibration to the prism, and after that they modes start to interact. But if the temperature maybe changes, it decreases this stabilized conditions, and the modes stimulates. It's not so powerful. So even if you mentioned continuous wave laser, in continuous wave it's like aim, create a good continuous wave laser. You can use titan sapphire laser like source the continuous wave laser, but it's not efficient because of course if you have it you can readjust the matching and you obtain it, but it's very expensive. You can go to the AliExpress and buy the laser pointer for that case, because it's cheaper and easier, because it's not support a lot of modes. Yeah, but there is a media which better for femtosecond lasers, and there is active media which is better for like semiconductors and so on, like neodymium yak media, which is better for narrowband.
So in continuous lasers we use materials which support only few modes, and in pulse lasers we use medias which support a lot of modes. Not a lot, but
exactly. Exactly.
Okay, thank you.
Okay, so I wait you information about chat, and as a response I